Somewhere in the old memory of the sky, a point of light kept coming back. It was not a star, though. From Earth, it could look like one through a telescope. It was not a planet, not a nearby explosion, not a small lamp inside our own galaxy. OJ-287 is the blazing heart of a distant active galaxy, a blazar where energy from near a supermassive black hole is aimed almost directly toward us. But what made it strange was not brightness alone. Many objects in the universe brighten, fade, flare, and vanish. OJ-287 seemed to do something more unsettling. Across decades of observations, and eventually across more than a century of old records, its brightest outbursts appeared to return in a rough rhythm, as if something hidden inside that distant galaxy were keeping time. Not perfect time, that is the key. OJ-287 did not behave like a clean clock on a wall. Its flares arrived unevenly, sometimes in pairs, sometimes near the expected moment, sometimes in ways that forced astronomers to rethink what they thought they were reading. The pattern was strong enough to suggest order, but difficult enough to resist a simple answer. One of the most famous explanations is astonishing. Perhaps OJ-287 contains not one supermassive black hole, but two. Perhaps a smaller black hole moves around a larger one on a long tilted orbit, and at certain moments it plunges through the larger black hole's disk of hot gas and plasma. The disk responds with a flare, and billions of years later, that ancient light reaches Earth as a flash in our telescopes. Yet even that image is only the beginning. OJ-287 is also a Blazar with a powerful jet pointed toward us, and that jet may both reveal the system and hide the very clock we are trying to understand. Its light is a clue, but also a glare. Its rhythm is a guide, but also a puzzle. Tonight we will follow OJ-287 as a slow cosmic investigation. We will begin with the returning light. Enter the archive where the clock was found, step into the impact model. Watch astronomers wait for predicted flares, and finally confront the jet that complicates everything. If there is a clock inside this distant Blazar, what is making it tick? And why does its failure to tick evenly tell us more than a perfect rhythm ever could? Long before OJ-287 became a famous cosmic mystery, it was only a point of light, not a bright planet in the evening sky, not a nearby star with a name carried through human culture, not something the unaided eye could pick out from a quiet field on Earth. It was a faint source in the deep background of the universe, recorded by instruments as one small mark among countless others. And yet that mark kept changing. From Earth, OJ-287 looks almost impossibly small because distance compresses an entire active galaxy into a single point of brightness. It is not a star, although it can appear star-like through a telescope. It is the blazing center of a distant galaxy, a blazar where energy from the region around a supermassive black hole is aimed almost toward us. That simple fact already makes it extraordinary, but it is not the reason OJ-287 became one of astronomy's strangest long-term puzzles. The reason was time. Again and again, across the record of observation, OJ-287 brightened. It did not brighten in a calm, smooth, predictable way like a lamp slowly being raised and lowered. It flared. It rose above its ordinary state, sometimes dramatically, as if some hidden engine inside the distant galaxy had suddenly released a new surge of energy. Then it faded again. At first, a single flare could be only that one flare. Active galaxies are restless by nature. Their light can rise and fall because matter near a black hole is turbulent because jets change direction, or brightness, because magnetic fields twist and release energy, because plasma, moving near the speed of light, does not behave like a steady flame. In such a place, brightness alone is not enough to create a mystery. But OJ-287 did something more patient. Its brightness returned across decades and then across more than a century of assembled records. Astronomers began to see that the strongest outbursts were not scattered entirely at random. They seemed to gather around a rhythm, a recurring interval of roughly 12 years. Not perfectly, not neatly enough to be mistaken for a mechanical clock, but often enough, and strangely enough, that the pattern began to feel like a message hidden inside light. Imagine looking at the sky, not for one night or 1 year, but through the memory of generations. One observer records a faint object. Another years later sees it brighter. A later survey catches another brightening. Old photographic plates made for broad surveys of the heavens preserve tiny traces of the same distant source in silver and shadow. Each record is small. Each record alone seems almost ordinary. Then slowly the pieces are placed beside one another. A curve begins to form. It is not a line drawn through space, but a line drawn through years. It shows the changing brightness of OJ-287, rising and falling, quieting and returning. In that curve, astronomers did not see a calm object. They saw something that seemed to remember. Of course, OJ-287 does not remember. It has no intention, no awareness, no message shaped for human minds. Its behavior is governed by gravity, plasma, radiation, magnetism, and motion. But from our side of the universe, where light arrives late and meaning arrives later, still, the repeated flares feel almost like a memory preserved in brightness. Something far away was not simply flickering, it was coming back. Somewhere billions of years in the past, in the heart of a remote galaxy, an event released light. That light traveled through expanding space long before it reached human instruments. It crossed darkness while Earth changed, while life evolved, while civilizations appeared and vanished, while telescopes were invented, improved, and lifted above the atmosphere. When the light finally arrived, it did not come with an explanation. It came as a point growing brighter. Then years later, another flare arrived. Then another. To us, those flares seem separated by human time decades, careers, generations, long waits between one brightening and the next. But in the distant system itself, they may belong to motion. Something may be orbiting. Something may be crossing a disk. Something may be disturbing gas near a black hole so massive that ordinary images of scale fail almost immediately. At this stage, we do not need to solve the mystery yet. It is better to stay with the strangeness of repetition. A single explosion can be dramatic. A repeating signal is more unsettling. It suggests structure beneath violence. It suggests that the outburst is not only an accident of chaos, but the visible trace of a deeper pattern. When a source like OJ-287 flares again and again, the mind begins to ask what kind of cosmic arrangement could make catastrophe return. But the schedule is imperfect. If OJ-287 brightened every 12 years with exact precision, like a clock on a wall, the mystery might be easier to hold. Astronomers could search for one clean mechanism, one repeating orbit, one timed event, and then fit the data around it. But OJ-287 does not behave with that kind of obedience. Its great flares arrive with irregular spacing. Some appear paired. Some seem early or late. Some predictions become triumphs. Others become questions. The clock ticks, but not evenly. That is why OJ287 is more than a curiosity. A perfect rhythm would be beautiful, but a flawed rhythm can be more informative. In the unevenness, there may be clues about gravity, orbit-shaped disk structure, jet behavior, and the slow changes that occur when enormous objects move through one another's gravitational fields. For astronomers, this is the difference between watching a light and reading a system. A light tells you that something happened. A repeated light tells you that something may be happening again and again. An uneven, repeated light tells you that the system is not simple and that every return carries a slightly different history. It asks not only why it brightened, but why it brightened then. Why then? Why did the light rise at those particular times? Why did some outbursts arrive as if they belonged to a larger cycle? Why were they not spaced with perfect regularity? Why would an active galaxy behave as if it were both chaotic and ordered at once? The most famous answer will come later in our journey. Perhaps OJ287 contains two supermassive black holes, not one. Perhaps one black hole moves around another on a tilted, elongated orbit. Perhaps at certain moments, the smaller one plunges through the disk of gas around the larger one, creating a flare that we see long after the event itself occurred. But at the beginning, before the model, there is only the returning light. And that returning light is already enough to disturb the imagination. Because in astronomy, time is often the instrument. Telescopes collect light, but patience collects meaning. A night of observation may show a source. A decade may show a change. A century may reveal a pattern that no single observer could have held inside one lifetime. OJ287 belongs to that slower kind of discovery. It asks science to wait. It asks observers to keep records, even when the meaning is not yet obvious. It asks later generations to return to old measurements with new questions. It asks human beings, whose lives are short, to recognize a rhythm that plays out on timescales just barely within reach of history. The universe is full of events that happen too fast for us, too slow for us, too far away for us, or too faint for us. Some vanish before we can turn a telescope toward them. Others take millions of years to unfold. OJ287 sits in a strange middle ground. Its central engine is remote and enormous beyond ordinary scale, but its outbursts return on a rhythm short enough that astronomers can wait for them. A person can begin a career during one flare and still be watching when the next one comes. That makes OJ287 feel almost conversational, although the conversation is not between equals. The Blazar does not speak in words. It does not know it is being observed. Its light was emitted long before the scientists who study it were born. Yet because its flares return, it gives astronomy something rare, a chance to ask a question, build a model, and then wait for the sky to answer. The answer is never simple. When the next brightening comes, it may confirm part of the model. It may arrive at the wrong time. It may appear in optical light, but behave differently in radio waves. It may be tangled with a jet hidden by glare, or interpreted differently by different teams. OJ287 keeps returning, but every return seems to bring both evidence and complication. The first observers did not need to know all of this. They only needed to record the light. A small mark on a plate, a brightness measured against other sources, a flare noted in the sky. These acts may seem ordinary, but they are the foundation of the entire mystery. Without the habit of keeping records, OJ287 would be only another variable source. Without old observations, the rhythm would have no depth. Without time, the clock could not be seen. Light from OJ 287 kept arriving at Earth in great pulses of brightness. Each pulse was already ancient by the time it touched our instruments. Each had begun its journey when the distant system was in a different state, when the possible orbit had carried hidden objects into a new arrangement. To observe OJ 287 is not to watch something happening now in the ordinary sense. It is to receive delayed evidence from a remote past. And still, because the evidence repeats, it feels alive. A flare in the early 20th century can speak to a flare decades later. A brightening in the 1970s can be compared to one in the 1980s. A prediction made in one decade can be tested in the next. Modern telescopes can revisit old questions with ultraviolet X-ray, gamma ray, and radio observations, adding new layers to a pattern first noticed in visible light. By now, OJ 287 is not just a point in the sky. It is a long story written in brightness. It has quiet intervals and sudden rises. It has repeated themes and strange variations. It has enough order to suggest a clock, and enough disorder to keep that clock from becoming simple. That balance is the reason we keep listening. If OJ 287 were only chaos, the story might dissolve into noise. If it were only order, the mystery might end too quickly. But it is both a repeating flare from an unstable Blazar, a possible clock inside a storm, a rhythm shaped by forces we cannot see directly. So the first mystery is not simply why OJ 287 brightens. The first mystery is how any pattern survives in such a place. How can a system so extreme produce a rhythm that lasts across more than a century of observation? How can a Blazar known for violent variability also carry a repeating signature? How can astronomers separate the clock from the fire around it? To answer that, we have to understand what kind of fire this is. The light has returned. Now we have to ask what is shining. To understand the returning light of OJ 287, we first have to understand what kind of light it is. This is not the gentle light of a star burning steadily in nearby darkness. It is not the reflected glow of a planet or the slow fading of an ordinary explosion. OJ 287 is the active heart of a distant galaxy, compressed by distance into a point, but powered by one of the most violent engines the universe can build. It is a Blazar. The word may sound technical at first, but the image behind it is simple enough to feel. Imagine a galaxy with a supermassive black hole at its center. Around that black hole, gas dust and plasma fall inward, not calmly, but in a flattened, rotating disk, heating as gravity pulls it into tighter and faster motion. Near the central region, some of that material does not simply disappear. Part of it is launched outward in narrow jets racing away from the black hole's surroundings at nearly the speed of light. A Blazar is what we call such an active galactic nucleus when one of those jets points almost directly toward us. This changes everything. If the jet were aimed sideways, we might see OJ 287 as a powerful but less extreme active galaxy. Because the jet is aimed close to our line of sight, its light is intensified by relativistic effects. The plasma is moving so fast toward us that its radiation is boosted, brightened, and made more dramatic. It is as if the universe has turned a cosmic searchlight toward Earth. That is why OJ 287 can be visible across such immense distance. It is not close. Its light has traveled for billions of years before reaching our telescopes. The galaxy that produced that light lies so far away that ordinary imagination begins to fail. And yet, because its central engine is powerful, and because its jet is directed nearly toward us, OJ287 becomes a detectable point in the sky, a faraway fire whose changes can still be measured from Earth. But the same fire that reveals it also makes it difficult to understand. A Blazar is not a quiet lamp. It is a storm pointed at us. Its brightness can change because material moves within the jet, because shocks travel through plasma, because magnetic fields twist and release energy, because the disk feeding the black hole changes, or because the direction and structure of the jet shift slightly over time. To watch a Blazar is to watch a lighthouse whose beam is made of violent matter and whose lantern sits near a black hole. So, when OJ287 brightens, the first question is not only what happened, the first question is which part of the system we are seeing. It could be the disk, it could be the jet, it could be a disturbance caused by an orbiting companion, it could be several things overlapping at once. From Earth, all of that complexity arrives as a change in brightness, a flare in optical light, radio waves, ultraviolet X-rays, or gamma rays. The signal is rich, but it is not simple. This is why OJ287 is both generous and evasive. It gives us light, strong enough to study, but it gives that light through a system that does not separate its pieces neatly for us. The jet may dominate the view so strongly that other sources of radiation become difficult to see. The accretion disk may be present, but hidden beneath the glare. A possible second black hole may leave signs, but only indirectly through timing. Outbursts and disturbances in matter we cannot resolve in a simple image. At the center of this confusion is the supermassive black hole itself. A black hole does not shine by its own surface because it has no surface in the ordinary sense. The event horizon is not a glowing wall. It is the boundary beyond which light cannot return. If a black hole were truly alone with no gas, no stars, no disk, and no jet around it, it would be nearly invisible. The brightness comes from what the black hole does to its surroundings. Gas falling inward loses gravitational energy. It heats, it collides, it spirals. It becomes plasma. In the accretion disk, matter can reach extraordinary temperatures and radiate fiercely before some of it crosses the point of no return. Near the central regions, magnetic fields may help channel energy into jets launching streams of particles outward along the rotation axis of the system. The black hole is dark, but the neighborhood is ablaze. That is the first paradox OJ287 asks us to hold. We are trying to study one of the darkest kinds of objects in nature by watching one of the brightest kinds of cosmic light. The darkness at the center creates conditions so extreme that the surrounding material becomes luminous enough to be seen across billions of years. And in OJ287, that light does not merely shine, it varies. Some changes may be small and restless, like the flickering of a turbulent flame. Others are grand outbursts rising above the usual activity and becoming important markers in the long record. For the story of OJ287, the great question is how to distinguish ordinary Blazar variability from something deeper, something that repeats because of a hidden orbit. If it were a quiet object, a repeating flare might be easier to interpret. If almost nothing changed except a 12-year outburst, the clock would stand out more cleanly. But OJ287 is not quiet. It is already active, unstable, and full of brightness that can surge and fade for multiple reasons. The clock, if there is one, is hidden inside weather. Not weather of air and clouds, but weather of plasma, magnetic fields, radiation, and gravity. Energy moves through the jet. Shock fronts may travel outward. Regions of plasma brighten, fade, and interact. Radiation arrives at different wavelengths, each carrying a different layer of the system. For the listener on Earth, this means OJ287 is not a simple blinking beacon. It is more like a storm-lit lighthouse on a distant coast where the beam, the lightning, the fog, and the waves all arrive together. The challenge is to find the rhythm underneath. Astronomers do this by watching OJ287 not only in visible light, but across the electromagnetic spectrum. Optical telescopes trace brightness changes similar to what older observations preserved on photographic plates. Radio telescopes listen to the jet and its structure. Ultraviolet and X-ray observations may probe higher energy processes closer to the active core. Gamma rays can reveal some of the most energetic events in the jet. Each wavelength is like a different instrument listening to the same distant orchestra. No single one tells the entire story. Optical light may show a flare, but not fully explain its origin. Radio waves may reveal jet activity, but not directly show the disk impact. X-rays may brighten for reasons tied to high-energy particles or inner regions of the system. Together, they create a more complete and more complicated picture. This is one reason OJ287 has remained fascinating for so long. It refuses to become only one thing. It is a blazar. It may be a binary black hole system. It may show disk impacts. It has a jet that can dominate the light. It has long-term patterns and short-term surprises. It carries the promise of a cosmic clock, but keeps that clock behind layers of fire. To say that OJ287 is a Blazar is therefore not a side detail. It is central to the mystery. The jet explains why we can see the source so clearly from such an enormous distance. It also explains why the source is so difficult to read. The same alignment that makes OJ287 bright also floods the observation with jet-driven variability. We are not looking at the system from a calm angle. We are looking almost down the barrel of its most energetic outflow. Somewhere in the distant universe, a galaxy holds a central engine. Near that engine, matter spirals inward. Above and below the disk jets burst outward along a cosmic axis. One of those jets is aimed close enough toward Earth that its radiation is magnified into one of the most intense signals we can study. Across billions of years, that light travels through space and reaches our instruments as a flickering point. Inside that point, an entire galaxy is being reduced to a pulse. This is the strangeness of astronomy at cosmic distance. A whole active nucleus becomes one source. A jet many light years long becomes a feature inferred from radio maps and brightness changes. A region where black holes may be orbiting becomes a mathematical model, a timing pattern, a set of flares. We do not receive the full scene, we receive evidence. In the case of OJ287, the evidence begins with brightness that returns. But to interpret that return, we have to ask whether the outbursts belong to the jet, the disk, an orbit, or some combination. The Blazar is not merely a stage on which the mystery happens. It is an active participant in the mystery. This is why later observations have complicated the older, cleaner picture. A simple version of the story might say a smaller black hole crosses the disk of a larger black hole, the disk flares, and we see the impact. That may describe an important part of the model, and it gives the imagination something powerful to hold. But OJ287 is more difficult than that. If the jet is changing, if the jet is brightening, if the jet is pointed toward us and amplified by relativistic motion, then some flares may not come cleanly from the disk at all. The light may be telling more than one story at once. That does not make the clock meaningless. it makes the clock harder to isolate. Think of trying to hear a slow bell ringing inside a city at night. The bell is real, perhaps, but around it are engines, voices, rain, wind, and distant sirens. The task is to separate one pattern from all the others. Astronomers do something similar with OJ287. They compare the timing of flares. They examine colors and wavelengths. They look for whether an outburst is thermal, suggesting hot material in or near the disk, or non-thermal, suggesting energetic particles in the jet. They study polarization because the orientation of light can reveal magnetic fields and jet structure. They build models, then wait for the object to test those models with the next return. This is why OJ287 is not only beautiful as an image, it is beautiful as a problem. Every part of it demands patience. The jet must be understood before it can be separated from the disk. The disk must be modeled before an impact can be interpreted. The possible orbit must be reconstructed before timing can become evidence. And all of this must happen with light that left the source billions of years ago. The result is a kind of cosmic detective work conducted through delay. Nothing about OJ287 happens for us when we see it. The flare we record tonight began long before our civilization existed. The jet whose radiation reaches us now belonged to an ancient state of the distant galaxy. Yet because the pattern repeats the past, becomes testable. We cannot touch OJ287, but we can wait for its next clue. That waiting depends on understanding the fire. If we mistake every jet flare for a disk impact, the clock becomes false. If we dismiss every repeated flare as ordinary Blazar chaos, the clock disappears. The truth may lie in careful discrimination. Some events may belong mainly to the jet. Some may carry the imprint of the disk. Some may reveal the timing of an unseen companion. Some may force the entire model to be adjusted. This is what gives OJ287 its long life as a mystery. It is not a puzzle solved by one definition. Calling it a Blazar opens the door but does not close the case. We are dealing with a source whose brightness is produced by alignment, speed, and violence. The signal is strong because the system is extreme. The signal is confusing for the same reason. The fire points at Earth. And within that fire, astronomers search for time. If OJ287 is already a storm of light, how did anyone find a clock inside it? How did scattered observations, old photographic plates, and decades of patient monitoring become a pattern strong enough to suggest hidden orbital motion? To answer that, we have to step into the archive, because the clock of OJ287 was not discovered in a single flash. It was assembled slowly from records of light that had been waiting in the dark. The clock of OJ287 was not found by watching one flare. It was found by going backward. Astronomy often feels like a science of the present moment. A telescope opens, a detector gathers light, a screen fills with data from the night. But many of its deepest patterns only become visible when the present is placed beside the past. A single observation can show that a source is bright. A second can show that it changed. Only a long record can reveal whether change itself has a hidden rhythm. OJ287 needed that long record. For much of its early life in astronomy, it was not yet understood as the extraordinary object we now discuss. It was a bright variable source in the sky, a distant point whose nature had to be inferred slowly. Like many astronomical objects, it left traces before anyone knew what those traces would later mean. Its light appeared on old photographic plates, preserved not as a grand cosmic message, but as tiny darkened marks in a survey of the heavens. Those plates became a kind of time machine. Before digital detectors, before space telescopes, before modern multi-wavelength campaigns, the sky was often recorded on glass. Photographic plates captured the positions and brightness of stars, galaxies, and strange sources whose importance might not be recognized for decades. Each plate was a frozen night. Each carried a piece of sky at a particular moment held in chemical memory. At the time, no single plate could reveal OJ-287's deeper secret. One plate might show it faint. Another might show it brighter. Another might miss a dramatic moment entirely. Weather telescope, sensitivity, exposure, time, sky conditions, and human intention all shaped what survived. The archive was not designed as a perfect story. It was scattered, incomplete, and uneven, like most memories. But sometimes an incomplete memory is enough. When astronomers later returned to those records, they were not merely looking at old images. They were asking a new question of old light. How bright was OJ-287? Then how did that brightness change? Did the outbursts appear randomly like sparks in a storm? Or did they gather around some recurring interval? Nothing about the old plates changed. The marks had been there for decades. What changed was the question. Once OJ-287 became interesting. As a variable object, once its later outbursts began to suggest a pattern, the old record turned into a map of earlier behavior. The past became newly useful. Slowly a light curve was built. A light curve is not a picture in the ordinary sense. It does not show a galaxy as a spiral, a nebula as a cloud, or a planet as a disk. It shows brightness across time. On one axis there is the passage of years. On the other, the rise and fall of light. It is a portrait of behavior rather than shape. For OJ-287, that portrait was restless. The source brightened and dimmed, as Blazars often do. There was noise, irregularity, confusion, and ordinary variability. But among the restless changes, larger outbursts stood out. They seemed to return after roughly 12 years, not with perfect discipline, but with enough repetition to become difficult to ignore. A clock began to appear inside the archive. It was not the kind of clock that hangs on a wall with clean seconds and obedient hands. It was more like a clock half buried under weather, a mechanism heard through wind. The rhythm could be sensed, but not neatly extracted. Some outbursts seemed paired, some arrived earlier or later than a simple period would suggest. The record itself had gaps. Yet the idea of recurrence remained. This was the crucial shift. OJ-287 was no longer just a source that flared. It was a source whose flares seemed to remember an interval. In the early 1980s, researchers examining the long-term record began to connect that recurrence with the possibility of a binary black hole system. The leap was not made from a single observation. It came from the pattern created when many observations were placed in sequence. If a single supermassive black hole could power a blazar, perhaps two black holes could create a repeating disturbance. Perhaps the outbursts were not only the random moods of a jet, but the visible consequence of orbital motion deep inside the active nucleus. That proposal changed the meaning of the archive. Old brightness measurements became possible footprints of an unseen orbit. A flare decades earlier could be compared with 1 decade later. The curve of light became a way of asking whether something massive was moving in a repeated path near the heart of the galaxy. This is how astronomy often turns absence into structure. No telescope could simply zoom in and show two supermassive black holes circling one another in OJ-287. The system was too distant, the central region too compact, the light too dominated by the Blazar jet. But if the motion affected the light, then the motion might be reconstructed indirectly. The clock, if real, was not seen as a pair of objects. It was seen as timing. Timing can be a surprisingly powerful form of vision. We use timing whenever distance scale or darkness prevents direct sight. The rhythm of eclipses reveals orbital motion. The pulse of a variable star can reveal its nature. The wobble of a star can reveal an unseen planet. The arrival times of signals from pulsars can expose gravitational effects. In each case, time becomes a way of seeing what space hides. For OJ, 287 time became the first telescope capable of looking into the mystery. But this kind of seeing is fragile. A pattern in old data can tempt the mind. Human beings are very good at finding rhythm, sometimes too good. We connect points. We hear music in noise. We make stories from fragments. In science, a pattern must therefore do more than look suggestive. It must survive testing. It must make predictions. It must explain not only what has already happened, but what should happen next. That is why the archive was only the beginning. The early recognition of a possible 12-year cycle did not settle the case. It opened it. If the outbursts were tied to orbital motion, then future outbursts should not appear at just any time. Their timing should carry information about the orbit. The shape of the orbit, the mass of the black holes, the structure of the disk, and relativistic effects might all alter when a flare appears. The clock could be tested by waiting. This gives OJ 287 a rare narrative power. Many astronomical discoveries are complete in the sense that we observe something after it has happened and then explain it as best we can. OJ 287 invites a more dramatic form of patience. A model can be built, a future flare predicted, and then astronomers must wait for the sky to answer. The archive looks backward. Prediction looks forward. Between the two sits the model. At first, the simplest temptation is to imagine a strict 12-year period, flare, wait 12 years, flare again. But OJ 287 does not allow that simplicity. Its record shows a more complicated pattern, including pairs of outbursts and intervals that do not match a plain repeating cycle. This is where the idea of a binary black hole becomes both more difficult and more powerful. If one object were orbiting another in a simple circle, and if it produced one flare at the same orbital point, each time the timing might be cleaner. But the models proposed for OJ 287 are not so simple. They involve an elongated orbit, an orbit tilted relative to the disk, and a path that shifts over time under extreme gravity. The result is not a metronome. It is a gravitational clock whose hands are bent. Astronomers did not begin with the black holes. They began with the light. They began with the fact that OJ 287 had brightened before and before that and before that. They began with the old photographic marks, the modern measurements, the patient assembly of brightness across time. The possible black holes entered the story because the light seemed to require a hidden engine with memory. The archive gave the mystery a spine. Without it, a flare in the present might seem dramatic, but isolated. With it, the flare becomes part of a sequence. A single brightening says something happened. A repeated brightening says something is happening in a pattern. A pattern says there may be a structure beneath the event. This is why old data can become suddenly alive. A photographic plate stored for decades is not only an artifact of old astronomy, it is a piece of the universe's behavior preserved before the question was ready. When later scientists measure it again, they are not changing the past. They are allowing the past to speak in a new language. In OJ 287, that language was brightness. Imagine a researcher comparing measurements separated by half a human lifetime. One outburst sits in the record like a hill on a dark landscape. Another appears years later, then another. The spacing is imperfect, but not meaningless. The mind starts to ask whether these hills were made by the same moving cause, returning again and again to a dangerous crossing point. The clock was not discovered by a single heroic glance. It emerged from patient comparison. It required astronomers to believe that old records could still matter, that a point of light might carry a history longer than any one observer, and that a distant galaxy could be understood not only by how bright it is, but by when it brightens. OJ 287 does not choose when to brighten. The language of choice is only metaphor. The Blazar is not remembering. It is not signaling. It is not keeping time for us. Its behavior is governed by matter, gravity, magnetism, motion, and radiation. But from our side of the universe, where light arrives late and interpretation comes later, still, the repetition feels almost intentional. That feeling is useful as long as we do not mistake it for explanation. Science begins by allowing wonder, then asking what kind of mechanism could make the wonder real. The repeating light was the wonder. The binary black hole hypothesis was one attempt to give it a mechanism. But between wonder and mechanism lies the careful work of evidence. That work is still ongoing. Even today, the clock inside OJ 287 is not read in only one way. Some researchers emphasize the disk impact model. Others focus strongly on the jet. Some observations support one aspect of the binary picture, while others complicate the mass estimates or the interpretation of particular flares. The archive did not give a final answer. It gave a long enough question, and that may be even more valuable. A short question can be answered quickly. A long question changes the field around it. OJ 287 has forced astronomers to combine historical light curves, optical monitoring, radio observations, space telescopes, high-energy data, jet studies, and relativistic modeling. It began as a repeated brightening and became a meeting place for many kinds of astronomy. The old plates could not have predicted that. They simply held the light. In that sense, the archive is humble. It does not explain. It preserves. It waits for later minds, later tools, later theories. The marks on a plate do not know whether they are recording a star, a galaxy, a blazar, or the possible influence of two supermassive black holes. They are evidence before interpretation. OJ 287 reminds us how often science depends on that kind of patience. To find a clock inside the archive, astronomers had to connect observations made by different people with different instruments under different conditions. They had to compare brightness across decades and correct for the unevenness of the record. They had to decide whether the pattern was strong enough to deserve a physical explanation. That is not a simple act of seeing. It is a slow act of reconstruction. Once the reconstruction began, the story of OJ 287 changed forever. The source was no longer only a Blazar pointing its fire at Earth. It became a possible machine of time light and gravity. Its flares became markers. Its quiet periods became intervals. Its irregularities became clues. Its future became testable. The clock was not made of gears. It was made of events. Its face was not visible. Its hands were not seen. Its ticking was not audible. It existed as a relationship between flare and flare, between old data and new prediction, between hidden motion in a distant galaxy and patient human record-keeping. But a clock once found demands an explanation. What could make a Blazar flare in this repeated uneven way? What kind of hidden object could return to the same dangerous region again and again? How could an orbit produce not a quiet signal, but a burst of light so intense that it can cross billions of years and still reach our telescopes. The archive gave us the rhythm. Now we have to ask what strikes the beat. The archive gave us the rhythm. Now the question becomes, what could strike the beat? J. 287 is already a violent object by nature. As a blazar, it can brighten because its jet changes, because shocks move through plasma, because magnetic fields twist and release energy, or because matter near the central black hole becomes unstable. But a roughly repeating pattern asks for something more than ordinary restlessness. It asks whether there is a hidden motion behind the light, something returning again and again to a dangerous place. The most famous answer is the impact model. In this model, OJ287 does not contain only one supermassive black hole at its center. It contains two. One is the primary enormously massive, surrounded by a disk of gas and plasma spiraling inward under gravity. The other is smaller, though still gigantic by any human standard, moving around the first on a long, tilted, elongated orbit. Most of the time, this second black hole is invisible to us. It does not shine like a star. It does not have a glowing surface. It moves through the central region as a dark body, whose presence must be inferred from what it does to the material around it. At certain moments in its orbit, it is thought to pass through the accretion disk of the larger black hole. That passage is the impact. The word must be handled carefully. This is not an impact like a stone striking the ground. It is not two solid objects colliding. A black hole has no surface in the ordinary sense, and an accretion disk is not a flat, rigid plate. It is a rotating structure of hot gas dust and plasma shaped by gravity, heat, magnetic fields, and motion. So, when we say the smaller black hole impacts the disk, we mean that it plunges through or disturbs a dense region of orbiting material. Its gravity tears through the gas. It compresses heats and shocks the plasma. It may pull matter out of place and create a rapidly expanding bubble of hot material. The disk, already violent, is suddenly struck by the passage of an object millions or even hundreds of millions of times the mass of the sun. A flare is born from that disturbance. From Earth, we do not see the plunge itself. We do not watch the second black hole cross the disk like a dark needle through cloth. The system is far too distant, the region far too small on the sky, and the central light far too overwhelming. What we receive is the aftermath, a surge of radiation delayed by billions of years, arriving as a brightening in the long record of OJ287. This is what makes the model so powerful as an image. A hidden object moves through a hidden disk. The event itself is invisible. The disk reacts, and the reaction becomes light. The light crosses the universe, enters telescopes on Earth, and appears in the archive as one more peak in the curve. The clock in this picture is orbital. The repeated flares are not random bursts from a restless engine. They are markers of the smaller black hole returning to the disk. Each time its orbit brings it through the material surrounding the primary, it leaves a bright signature. If it crosses the disk twice during one orbit, the record may show pairs of outbursts rather than a single simple peak. That possibility helps explain why OJ287's rhythm is not clean. The old idea of a 12-year cycle is useful, but it is only the beginning. In the impact model, the smaller black hole is not moving in a neat circular path. Its orbit is stretched, tilted, and changing under the influence of extreme gravity. It may cross the disk at two different points, and the time between those crossings does not have to be equal. This makes the clock stranger, but also more informative. If the flares came with perfect simplicity, they would tell us less. Their uneven timing may carry information about the orbit itself. The delays, shifts, and pairs become clues. The very imperfection that makes the pattern difficult is what allows astronomers to ask about the masses of the black holes, the orientation of the disk, and the relativistic changes in the orbit. In other words, the impact model does not erase the irregularity. It uses it. To feel the scale of the model, it helps to slow down the scene. Imagine the central region of OJ 287, not as a still diagram, but as a place of motion. Around the primary black hole, material spirals in a hot disk. The disk is not calm. It is thick with energy friction, turbulence, and magnetic structure. Above and below it, a jet may be launched outward, one side aimed close enough toward Earth that its radiation is strongly amplified. Through this already extreme environment, the second black hole moves on its long orbit. It is not a planet moving around a star in a clean solar system. It is a massive, compact object moving through the warped gravitational field of another massive, compact object. The orbit carries it above and below the disk plane. Then at the crossing, it dives through the disk's material. The passage is brief compared with the full orbit, but the consequences are large. Gas is disturbed, energy is released, a flare begins its long journey toward us. There is a strange quietness in the way we observe such violence. At the source, if the model is right, the event is enormous. Matter is heated under conditions far beyond anything on Earth. Gravity curves space-time. Plasma is thrown into disturbance. Yet on Earth, the result may first appear as a number in a dataset, a point on a graph, a rise in brightness recorded by an instrument. The violence becomes measurement. This is one of the central beauties of astronomy. The universe performs events beyond direct human experience, and we receive them as traces. A flare is not the event itself. It is the messenger. It tells us that something changed, that energy was released, that a hidden configuration may have reached a crucial crossing point. For OJ 287, the impact model turns those messages into a possible sequence. A flare is not only a flare, it may be the mark of a crossing. A pair of flares may mark two disk passages. A delay may mean the orbit has shifted. A mismatch may mean the disk structure mass estimate or jet contribution has been misunderstood. Every brightening becomes a way to test the architecture of an invisible system. This is why the model became so compelling. It offered an answer that could be tested against time. If the smaller black hole truly follows a particular orbit, and if flares occur when it crosses the disk, then astronomers should be able to calculate future crossings. They should be able to predict when the next major outburst might occur. The model would no longer be only an explanation of the past. It would become a wager on the future. That is a rare and powerful thing in the study of distant galaxies. Many cosmic explanations are retrospective. Something happened, and scientists reconstruct why. OJ 287 gives the possibility of prediction. The sky can be asked to return with evidence. A flare can be expected. A window can be watched. Telescopes can be prepared. If the flash appears near the predicted time, the model gains strength. If it does not, the model must be revised. Still, we should not make the model sound cleaner than it is. The impact picture is famous, useful, and deeply visual. But OJ 287 is not a laboratory apparatus built for our convenience. It is a Blazar. Its jet can flare for reasons unrelated to disk impacts. Its accretion disk may be difficult to see directly because the jet is so bright. Different wavelengths may tell different parts of the story. Different teams may weigh the central black hole differently or interpret the timing in different ways. The impact model is not a finished statue. It is a working structure. A working model can be strong without being final. It can explain many features while still leaving some unsettled. It can make successful predictions while still needing adjustment. It can guide observation, sharpen questions, and organize evidence even as newer data complicate parts of it. OJ-287 demands that kind of humility. When we imagine the smaller black hole crossing the disk, we are giving shape to something we cannot directly see. That image is valuable because it makes the timing meaningful. But the image must remain tied to evidence. The flare's color, duration, energy, wavelength, behavior, and relation to the jet all matter. A true disk impact should not be treated the same as every kind of Blazar flare. This is where the story becomes more subtle. The impact model is not only about one dramatic plunge, it is about separating signal from noise in one of the noisiest possible environments. It is about asking whether a repeating disturbance can survive inside a jet-dominated Blazar. It is about using the disorder of light to infer an order of motion. A good metaphor might be a bell struck inside a thunderstorm. The thunder is real, the wind is real, the rain is real. But somewhere inside that violent weather, a bell may still be ringing at intervals. To prove it, one must record patiently, compare carefully, and avoid mistaking every loud sound for the bell. OJ-287 is the storm, the impact model is the bell. If the model is right, the bell is not made of metal, it is made of orbit. The second black hole returns. It crosses the disk responds, the flare appears, then the system continues altered slightly by gravity motion, and perhaps the slow loss of energy through gravitational waves. A system of two supermassive black holes is not static. Their orbit can evolve. In the most extreme cases, gravitational waves carry energy away from the system, changing the path over time. In OJ-287 models have attempted to include such effects, using the timing of flares to infer not only where the companion is moving, but how the orbit itself changes. This is why the impact model leads beyond spectacle. At first, it gives us the image of a repeating cosmic impact. Then it becomes a tool for measuring gravity. The flare is no longer only an explosion of light. It is a timestamp. It tells us where the hidden companion may have been when it crossed the disk and how the orbit has shifted since earlier crossings. The light becomes a clock hand, but unlike a clock hand made of brass or steel, this one is made of plasma delay and inference. It does not move smoothly around a face. It appears only when the system releases enough energy for us to notice. Between flares, the clock is hidden. The great events are not visible as events. They are reconstructed afterward. Astronomers collect light, compare it with models, adjust orbital parameters, examine the timing, and ask whether the system behaved as expected. The more successful the prediction, the more tempting the model becomes. The more complicated the data, the more carefully the model must be held. There is no simple ending here, and that is good for the story. If the impact model solved everything immediately, OJ-287 would become less interesting. Instead, it gives us a central image and then opens new questions. How massive is the primary black hole? How exactly is the disk shaped? How does the jet interfere with what we see? Which flares are disk impacts and which belong to jet activity? How much does general relativity alter the orbit? How much energy is being lost from the system over time? The impact model is not a door closing. It is a door opening into deeper physics. For the listener, the most important thing is to hold both parts at once. The model is vivid. A secondary supermassive black hole plunges through the disk of a larger one, creating a flare that repeats as the orbit returns. The model is also careful. This is an interpretation built from timing light curves, multi-wavelength data, and theoretical calculations, not a direct movie of the event. We are not watching the impact. We are reading its possible echo. That echo has shaped the way astronomers think about OJ-287 for decades. It has turned a strange repeating Blazar into one of the strongest candidates for a supermassive black hole binary. It has allowed predictions that could be compared with future flares. It has made the system a potential testbed for some of the most extreme gravitational physics available outside the imagination. Yet it has also forced science to remain patient. Every clock must be checked. Every predicted flare must be observed. Every interpretation must survive the next return of light. In OJ287, the model does not stand apart from the sky. It waits beneath it, exposed to whatever the next outburst will reveal. This is why the impact model belongs at the center of the documentary, but not at the end of it. It gives us the great image, a dark companion crossing a disk of fire. It gives us the mechanism, repeated disturbance from orbital motion. It gives us the possibility of prediction future flares as tests of the model. It also gives us the next mystery, because the clock it describes does not tick evenly. The crossings do not come like simple anniversaries. The orbit shifts, the timing bends, the flare pattern changes, gravity itself may be altering the rhythm. If we want to understand OJ287 more deeply, we have to stop thinking of the clock as a neat circle and begin thinking of it as a distorted path through curved space-time. The impact model tells us what might be striking the beat. Now we have to understand why the beat refuses to stay even. The impact model gives OJ287 a rhythm, but it does not give it a simple rhythm. If the story were only that a smaller black hole circles a larger one and strikes the disk every 12 years, the mystery would become almost too clean. We could imagine a cosmic clock with one hand, one orbit, one expected flare, returning with calm precision across the centuries. The sky would brighten on schedule. The archive would confirm the pattern. The model would settle into place. OJ287 does not offer that kind of comfort. Its light returns, but not with perfect obedience. The major outbursts seem connected by a rough cycle, yet they do not arrive like anniversaries. Some appear in pairs. Some seem separated by shorter intervals, others by longer ones. Some outbursts fit predictions well enough to strengthen the binary model, while others force astronomers to adjust the way they read the system. The clock ticks, but the ticking bends. That bending is not a weakness in the story. It is the story, because if OJ287 really contains two supermassive black holes, then the system is not a neat machine turning in empty space. It is a place where gravity is strong, motion is fast, the disk is disturbed, the jet is blazing, and even time and orbit cannot be treated as simple background. A clock on Earth works because its parts are small, local, and controlled. OJ287 is nothing like that. Its possible clock is made of a black hole orbiting another black hole. The hand is not metal. It is a compact object moving through curved space-time. The clock face is not fixed. It may be an accretion disk whose structure changes over time. The tick is not a sound. It is a flare of radiation from disturbed gas arriving at Earth after crossing billions of years of space. So, when the timing is uneven, the first question should not be why the clock is broken. The better question is what the unevenness is trying to tell us. In the impact model, the smaller black hole does not move in a perfect circle. Its orbit is elongated more like a stretched oval than a ring. This means its speed changes as it travels. When it moves closer to the primary black hole, gravity pulls it faster. When it moves farther away, it slows. Because the orbit is tilted relative to the disk, the smaller black hole does not simply stay inside the disk, like a planet moving in the same flat plane as the material around it. It passes above and below. At certain points, it crosses through the disk. Those crossings may happen twice during one long orbital cycle, but the spacing between them does not have to be equal. This is one reason OJ287 can show paired outbursts. One crossing can occur producing a flare. Then after some interval, the companion can cross the disk again. Because the orbit is stretched and inclined, the interval between crossings may be short in one part of the cycle and much longer in another. The same orbit can produce a rhythm that repeats in a broad sense, but feels uneven in the details. The hidden motion is periodic, but the visible flares are not evenly spaced. That distinction is essential. A system can have an orbit and still produce an irregular light curve. The orbit may repeat, but the conditions of each encounter may differ. The disk may be thicker or thinner at the crossing point. The companion may pass through at a different angle. The disturbed material may take time to expand, heat, cool, and radiate. The jet may brighten at the same time, confusing the view. A flare is not only a date on an orbital calendar, it is the final visible result of many physical processes. This is why predicting OJ287 is so difficult. Astronomers are not simply calculating where one object is. They are trying to connect hidden orbital motion to a burst of light produced by gas plasma radiation and delay. Between the crossing and the observed flare, there may be a chain of events that is still imperfectly understood. The companion may pass through the disk at one moment, but the light we see may rise after the disturbed material has expanded or changed. The flare may be affected by how dense the disk was at that location. It may depend on the temperature, opacity, and geometry of the gas. It may be blended with ordinary Blazar activity. The clock is not read directly from the black hole's position. It is read from the system's reaction, and reactions take time. Then there is gravity itself. Near supermassive black holes, gravity is not merely a force pulling objects together in the simple Newtonian picture. Einstein's general relativity changes the deeper structure of the story. Massive objects curve space-time, and objects moving through that curved space-time do not trace the same path over and over like ink on a fixed page. Their orbits can precess. The point of closest approach can shift. The whole ellipse can slowly rotate. This precession is one of the reasons the clock does not tick evenly. If the smaller black hole's orbit shifts from cycle to cycle, then its crossings through the disk also shift. It will not strike the same places at exactly the same times in a simple repeating pattern. The disk is there, the orbit returns, but the geometry has changed. A tiny change in the path can become a meaningful change in the timing of a flare. In OJ287, the proposed precession is not a decorative detail. It is central to the way some models attempt to explain the sequence of outbursts. The orbit is not only repeated, it is slowly reoriented by the gravity of the primary. The companion returns, but it does not return to an unchanged cosmic stage. The stage has turned slightly. This is where the imperfect clock becomes more interesting than a perfect one. A perfectly regular clock could tell us that something repeats. An irregular clock, if the irregularity follows physical rules, can tell us what kind of gravity is shaping the repetition. The departures from even timing can become measurements. A delay can speak, an early flare can speak, a paired outburst can speak. Each one carries information not because it is simple, but because it is not. There is another layer still. If two supermassive black holes are orbiting each other, they may emit gravitational waves. These waves are not light. They are ripples in space-time itself, produced when massive objects accelerate. In a system of enormous black holes over long periods, gravitational radiation can slowly drain energy from the orbit. The orbit can shrink. The timing can change. In OJ287, this possibility gives the flare record a deeper significance. If the outburst times are linked to the companion's orbit, then changes in those times may reflect how the orbit evolves. The system becomes more than a strange Blazar. It becomes a possible test of how gravity behaves when the masses are immense and the distances between them are relatively small on cosmic scales. This does not mean we should imagine gravitational waves as a loud sound shaking the galaxy in a way our ears could hear. They are not sound waves. They do not travel through air. They are changes in space-time moving outward at the speed of light. Their effect on the orbit, if correctly modeled, can be part of why the clock refuses to stay simple. So the uneven ticking of OJ287 may contain several layers at once. Part of it may come from the elongated orbit. Part may come from the tilt between the orbit and the disk. Part may come from orbital precession under general relativity. Part may come from energy loss through gravitational waves. Part may come from the structure and response of the disk. Part may come from the jet, adding its own flare-like behavior on top of the pattern. The result is not chaos. It is layered order. OJ287 is not interesting because astronomers see a perfect clock in the sky. It is interesting because they see enough recurrence to suspect a clock and enough imperfection to suspect that the clock is being shaped by extreme physics. The mystery is not destroyed by the irregularities. It is deepened by them. Think of a distant bell heard through a storm. If the bell rang with the mathematical clarity, the listening would be easy. But if wind, rain, thunder, and distance altered each sound, the task would change. The listener would not simply count the strikes. They would ask which sounds belong to the bell, which belong to the storm, and how the storm changes what the bell sounds like. OJ287 is that kind of listening. The flare record is the sound. The orbit is the possible bell. The jet disk and active nucleus are the storm. The uneven timing is not just interference. It is the combined voice of the whole system. This is why different teams can examine OJ287 and emphasize different parts of the story. Some focus on the long outburst pattern and the disk impact model. Some focus on multi-wavelength data and the jet's dominant role. Some debate the mass of the primary black hole because changing the mass changes the expected orbit, the disk, and the timing. The clock is there in the data, but the mechanism behind the clock remains a scientific argument, not a finished myth. That uncertainty should not make the listener distrust the story. It should make the story feel more real. Science does not become weaker when it admits that a distant object is hard to interpret. It becomes stronger when it names the difficulty and still searches for structure. OJ287 is difficult because it is far away, compact, energetic, and variable. It would be more suspicious if the answer were too neat. The universe rarely hands us a clean diagram. It gives us light. Then we ask, what kind of world could have produced it? For OJ287, the answer may be that a binary black hole system is producing a rough clock through repeated disk crossings. To make that idea work, the timing must be modeled with care. The orbit cannot be a simple cartoon. It must allow for precession-tilted geometry, and the fact that flares are not the crossing itself, but the radiative consequence of a crossing. In this way, the imperfect clock becomes a measuring instrument. It may help estimate the mass of the black holes. It may help test whether the orbit loses energy in the way general relativity predicts. It may help reveal the shape and orientation of the disk. It may even help place constraints on the nature of the primary black hole if the timing is accurate enough and the model is correct enough. That is an extraordinary idea. A source of light so distant that it is only a point in most observations may contain a record of gravity's behavior near two enormous black holes. The flare timing uneven and troublesome may be one of the only ways to read that behavior. The imperfection is not an obstacle standing outside the science. It is the data. Still, an imperfect clock can be misread. If one assumes too quickly that every major flare belongs to the impact model, one may force the data into a pattern it does not fully support. If one dismisses the recurring pattern too quickly as ordinary Blazar variability, one may lose the hidden orbit inside the noise. The challenge is to hold the model and the uncertainty at the same time. The mind wants either a clean answer or a clean rejection. OJ287 gives neither. It offers a model with remarkable explanatory power, but also observations that continue to complicate it. It offers predictions that have sometimes seemed impressively successful, but also later campaigns that force researchers to look again at jet activity, mass estimates, and the nature of particular outbursts. The clock continues to run, but the face is partly obscured. This is why the next flare always matters. Every new outburst is not just a spectacle. It is a test of accumulated assumptions. Did the model predict the timing? Did the flare appear in the expected wavelength? Did it look thermal, as if connected to hot disk material, or non-thermal, as if born in the jet? Did it have the right duration, color energy, and relation to previous activity? Did it arrive when the orbit said it should, or when the jet happened to surge? Each question turns a brightening into evidence. Each answer changes how the clock is read. The irregularity also changes the emotional shape of the story. A perfect clock would make astronomy seem almost passive. Scientists would simply wait for the next tick mark down and move on. An imperfect clock demands interpretation. It requires preparation, disagreement, patience, and revision. It makes the act of watching OJ287 feel alive. The sky is not merely repeating itself. It is negotiating with our models. That is why OJ287 belongs so naturally to long-form storytelling. Its mystery does not resolve in one explanation. It unfolds through time, and the unfolding itself is the subject. First, the returning light suggests a pattern. Then the archive reveals a rough clock. Then the impact model gives the clock a possible mechanism. Now, the uneven ticking tells us that the mechanism, if real, is shaped by gravity, disk physics, jet activity, and the limits of observation. A black hole system in a remote active galaxy may be moving through an orbit that takes years to complete. Its companion may cross a disk of hot plasma, creating disturbances that flare with tremendous power. The orbit may slowly rotate under relativistic gravity. Gravitational waves may carry away energy. A jet pointed toward Earth may blaze over the whole scene. And on our planet, astronomers wait for the light record, the timing, and try to infer the hidden dance. This is not a clock in the human sense. It is a cosmic process that only becomes a clock because human beings have learned to compare one flare with another. The universe does not label the ticks. We do that. We build the record. We test the intervals. We ask whether the irregularity follows rules. We decide whether the pattern survives the next observation. And if it does, the reward is not just knowing when OJ287 will flare. The reward is understanding why time itself seems bent into the brightness. The impact model tells us what might strike the beat. The uneven rhythm tells us how much more there is to learn from each strike. But a model, no matter how elegant, cannot remain safely inside equations. It has to face the sky. So, the next part of the journey is about waiting. Astronomers must take the imperfect clock seriously enough to make predictions. They must prepare their telescopes, watch through different wavelengths, and let OJ287 answer in its own ancient light. Sometimes the answer arrives close to the expected moment. Sometimes it arrives in a form no one fully anticipated. The clock does not tick evenly, but it keeps asking us to listen. The clock does not tick evenly, but it does return. That is what makes OJ 287 so unusual among distant cosmic mysteries? It is not only an object to be observed after something surprising has already happened. It is an object that allows astronomers to wait. A model can be built from old flares shaped by gravity and timing, and then placed before the future like a quiet question. Will the next flash come when the model says it should? In astronomy, this is a rare kind of tension. Many events in the universe are discovered only after they have already unfolded. A supernova appears, and then scientists reconstruct the life of the star that died. A gamma ray burst erupts, and telescopes turn toward its fading afterglow. OJ 287 offers something different because its great outbursts seem to recur. However imperfectly, astronomers can do more than look backward. They can prepare. They can calculate a window. They can arrange telescopes across the world and in space. They can decide what wavelengths to watch, what signatures to expect, what kind of flare would strengthen the impact model, and what kind would force the story to change. The sky becomes a test. There is something deeply human in that waiting. The central engine of OJ 287 is unimaginably far away. Its light has traveled for billions of years. The events being studied happened long before the astronomers watching them were born, long before telescopes existed, long before Earth's modern civilizations took shape. And yet, from our side of time, the flare can still feel like an appointment. A date approaches. Telescopes turn. The Blazar either answers or it does not. This is why prediction matters so much in the story of OJ 287. A model that only explains old data may be beautiful, but it can always be accused of fitting the past too closely. The real power comes when the model risks itself against a future observation. If a flare appears near the expected moment, especially with the expected qualities, the model becomes harder to dismiss. If the flare is absent, delayed early, or different in character, the model must absorb the difficulty. Every predicted flash is a trial. One of the most important modern moments came with the flares predicted around the middle and late 2010s. The impact model had grown more detailed over time, shaped by decades of outburst history and increasingly sophisticated calculations. It was no longer simply the idea that something happened every 12 years. It involved an orbit disk crossings precession, relativistic effects, and the timing of light produced after those crossings. A prediction is a brave thing in such a system. OJ 287 is a Blazar, not a quiet clock. Its jet can flare, its disk can vary, its light can change for reasons unrelated to the binary orbit. To predict a major outburst in that environment is to say that beneath all the storm, one specific mechanism should reveal itself at a specific time. The 2015 event became one of those tests. Astronomers watched for a flare that the binary black hole model had anticipated. When OJ 287 brightened close to the expected period, it was taken by supporters of the model as a significant success. The timing suggested that the underlying calculations were not merely arranged after the fact. They seemed to have reached into the future and found the next mark on the clock. But even a successful prediction does not end the story. It deepens it. A flare near the expected time raises new questions. Was its color consistent with a disk impact event? Was its duration right? Did it behave as expected across different wavelengths? Could the jet have contributed? Were there other outbursts nearby that complicated the interpretation? In OJ 287, prediction is never a clean finish line. It is the beginning of a more detailed argument. Then came 2019, one of the most cinematic moments in the recent history of the source. A predicted flare was expected when OJ-287 was in an awkward position in the sky. From Earth, and from many observatories near Earth, the source was too close to the sun's direction to observe easily. The sky itself was not dark enough around it. The Blazar was for practical purposes hidden behind the glare of our own star. But the Spitzer Space Telescope was not on Earth. By then, Spitzer was an aging observatory, moving in an Earth-trailing orbit around the sun. It had spent years studying the infrared universe, looking at dust stars, galaxies, exoplanets, and distant cosmic light. Near the end of its mission, it happened to occupy a position that allowed it to look toward OJ-287 when many other eyes could not. The old telescope was in the right place at the right time. Somewhere far beyond us, ancient light from a possible disk impact was arriving in the solar system. Earth-based observers were blocked by the sun's glare. Many instruments closer to Earth were poorly placed for the task. But Spitzer, drifting far from Earth, could still turn its gaze toward the source and catch the brightening. A cosmic clock was tested by a telescope near the end of its own lifetime. The flare observed in 2019 became another important piece in the argument for the timing model. For those who supported the binary black hole interpretation, it showed that the system's strange rhythm could be predicted with remarkable precision. The light did not simply return sometime near a vague cycle. It arrived close enough to make the model feel alive. Still, the lesson was not only triumph. The lesson was fragility. The flare could easily have been missed. If Spitzer had not been in that position, if the timing had not aligned, if the mission had ended earlier, if the observing plan had not been made, one of the most important tests of the model might have slipped past unseen. The universe does not wait for convenient viewing geometry. It does not move its signals away from the sun just because astronomers are watching. OJ-287 teaches that prediction is not enough. One must also be able to observe. This is why modern campaigns around OJ-287 are not built around one telescope alone. They require networks, timing coordination, and many kinds of light. Optical telescopes can watch the visible brightness. Radio observatories can trace the jet. Ultraviolet and X-ray instruments can catch higher energy behavior closer to the active nucleus. Gamma-ray observatories can reveal the most energetic particle processes. This multi-wavelength watching changes the emotional pace of the story. In the old archive, astronomers looked backward, gathering records after the fact. In modern campaigns, they look forward with preparation. They know the source may brighten. They know the window may be short. They know a critical flare might last days, weeks, or perhaps in some components far less. The waiting is no longer passive. It is organized. The next flash may not announce itself politely. It may rise quickly. It may appear in one band before another. It may be bright in optical light, but confusing in radio. It may come with gamma rays that suggest jet activity. It may look like a disk event at first, then reveal a more complicated structure. A source like OJ-287 does not provide one clean signal and stop. It gives layers. That is why the 2021 and 2022 observing campaigns matter in the broader story. Around that period, astronomers again watched OJ-287 closely, expecting behavior that could test the models. Some researchers interpreted parts of the activity as possible signs connected to the secondary black hole, including brief flashes and high-energy events. The idea was tantalizing, perhaps with dense enough monitoring. The hidden companion could reveal itself not only through long outburst timing, but through shorter, sharper signatures. But this is also where caution becomes essential. Not every flare proves the same thing. Not every brief brightening belongs to a disk crossing. In a Blazar, the jet can generate powerful events on its own. High-energy radiation can come from particles accelerated in the jet. Optical flashes can overlap with other changes. If a flare is very short, it may be precious evidence, but it may also be difficult to interpret without surrounding context. This is the discipline OJ287 demands. The excitement of a predicted flash must be balanced with the patience of analysis. The temptation is to say there it is, the secondary black hole. But the responsible story is more careful. The observations may support the model. They may fit some expectations. They may offer clues, but they must be compared across wavelengths, checked against jet behavior, and placed inside the full history of the source. The clock is being read through fire, and the fire can imitate the clock. This is one of the most important ideas for the listener to carry forward. The act of waiting for OJ287 is not like waiting for a train to arrive at a station. It is more like waiting for a bell inside a storm. You know when the bell might ring. You have a model for its rhythm. But thunder can sound at the same time. Wind can distort the sound. The bell itself may swing differently than before. When the next loud sound comes, the work begins. Was it the bell? Was it the storm? Was it both? For astronomers, a flare's timing is only one piece of evidence. Its spectrum matters. Its color matters. Its polarization may matter. Its relation to radioactivity may matter. Its X-ray or gamma-ray behavior may matter. Its duration matters. A flare that appears at the right time, but with the wrong physical character, is not the same as a flare that matches both timing and behavior. OJ287 is not kind enough to make every test simple. That is why it remains scientifically valuable. Because it only partly obeys, because it flares in ways that need interpretation, because its jet complicates the disk, because its timing can be both suggestive and troublesome. It keeps forcing the models to become sharper. The next flash is not only a confirmation, it is a revision tool. Each campaign can reveal what the previous model handled well and what it did not. Perhaps the timing was strong, but the wavelength behavior pointed to the jet. Perhaps the model predicted a flare, but a later analysis suggested a different origin. Perhaps a short event was missed in earlier cycles because no one had been watching continuously enough. Perhaps the historical record contains gaps that made the clock look cleaner or messier than it really was. In this way, waiting becomes a form of thinking. The time between flares is not empty. During those years, models are refined. Old data are remeasured. New instruments are prepared. Researchers debate mass estimates, orbital shapes, disk properties, and jet contributions. By the time the next observing window approaches, the question has changed slightly. OJ287 does not only repeat, it forces the observers to evolve. There is a quiet drama in that evolution. It does not look like a sudden explosion on a screen. It looks like years of preparation, months of monitoring, nights of observation papers compared with papers models corrected after new data. It looks like the scientific community learning how difficult it is to read one object honestly. The Blazar waits in the sky. The scientists wait on Earth. Between them is billions of years of light travel time and a narrow window of interpretation. The idea that a flare can test a model also gives OJ287 a philosophical weight. In science, prediction is one of the ways a theory earns trust. Not because every prediction must be perfect, and not because one success proves everything forever, but because prediction exposes a model to reality. It prevents explanation from becoming merely a story told after the fact. OJ287 has made astronomers expose their models again and again. Sometimes that answer is close enough to feel astonishing. Sometimes it is ambiguous enough to keep the argument alive. Both outcomes matter. The successful prediction can make the hidden orbit feel real. The ambiguous flare can remind us that the system is more complex than the orbit alone. The missed or altered prediction can open a new path, perhaps toward jet physics, perhaps toward a different disk model, perhaps toward a revised mass estimate. A failure is not always the end of a theory. Sometimes it is the pressure that makes the theory more honest. Popular accounts often want the simple version 2, supermassive black holes, one plunging through the disk of the other, producing a flare on schedule. That story is powerful, and it may capture something real. But the working science is richer. It includes prediction, uncertainty, dramatic disk impacts, jet-dominated emission, old light curves, and new multi-wavelength campaigns. When astronomers wait for the next flash, they are not waiting for a spectacle alone. They are waiting for discrimination. They are asking whether the source will separate its hidden components clearly enough for us to learn something. Will the disk announce itself? Will the jet overpower it? Will the timing match? Will the flare be bright, brief, delayed, or transformed? Every answer narrows the possible. Every answer also opens a new question. That is the rhythm of OJ 287 as a scientific story. The object brightens, scientists interpret. The model shifts. The next date approaches. Instruments prepare. The object brightens again or fails to brighten in the expected way. Interpretation resumes. The clock is not merely observed, it is negotiated over many returns. The waiting itself is part of the science, and perhaps that is why OJ 287 feels so different from many other cosmic objects. It allows human time to overlap just barely with black hole time. A 12-year rhythm is long but not unreachable. It is longer than most experiments, shorter than most cosmic cycles, and strange enough to make a career unfold in chapters of light. A student may begin by studying one flare. Years later, as a researcher, they may watch the next. Decades later, they may help refine the model for another. In that way, OJ 287 becomes not only an object in the sky, but a long relationship between human patience and cosmic recurrence. It teaches that the universe does not always reveal itself through one moment of brilliance. Sometimes it reveals itself by returning imperfectly and asking whether we have learned enough to understand the next return better than the last. But as the observations grow richer, one complication becomes impossible to avoid. The same Blazar jet that makes OJ 287 bright enough to study may also hide the very clock astronomers are trying to read. It can flare. It can dominate the emission. It can fill the signal with non-thermal light. It can turn a predicted window into a puzzle of overlapping causes. So, after waiting for the flash, the next task is harder. We have to ask whether the flash came from the clock itself or from the fire that surrounds it. After waiting for the flash, the next question becomes more difficult. What exactly flashed in OJ 287? A flare is never just a flare. It may look from Earth like a rise in brightness, a point of light becoming stronger against the dark. But inside that single brightening, several possible causes can overlap. A disturbance in the disk may release light. A possible companion black hole may trigger a crossing event. The jet may brighten for reasons of its own. The central engine may change in ways that do not fit neatly into any one model. This is why OJ 287 is so hard to read. The source does not give us separate labels. It does not say, this part came from the disk, this part came from the jet, this part came from the possible impact, this part came from ordinary Blazar turbulence. All of it travels across space and arrives as radiation. The task of astronomy is to separate the voices after they have already merged. And in OJ 287, the loudest voice may be the jet. A Blazar is powerful, precisely because one of its jets is pointed almost toward us. Plasma, moving near the speed of light, sends radiation along a narrow path, and when that path lies close to Earth's line of sight, the light is intensified. The jet becomes brighter than it would appear from another angle. It can dominate the object's appearance so strongly that the rest of the system is pushed into the background. This is the strange double role of the jet. It reveals OJ-287 by making it bright enough to study. It also hides OJ-287 by flooding the signal with its own activity. Imagine trying to study a small lamp behind a lighthouse beam aimed straight into your eyes. The lamp may be there, it may be changing in important ways, but the beam overwhelms the view, and every flicker you see has to be questioned. Did the lamp change, or did the lighthouse beam shift? Did the hidden source brighten, or did the glare in front of it surge? OJ-287 asks a similar question across cosmic distance. The possible clock of disk impacts may still exist. The smaller black hole, if it is there, may still cross the disk on a long and tilted orbit. But the jet is not a silent background. It is an active, violent, magnetized outflow, capable of producing its own flares and variations. It can imitate parts of the clock. It can obscure them. It can add its own rhythm to the pattern. This does not make the clock disappear. It makes it harder to isolate. The jet is made of plasma, not ordinary flame. It is a stream of charged particles and magnetic fields launched from the region near the black hole and accelerated outward at extreme speeds. Inside it, shocks can form. Knots of brighter material can move. Magnetic fields can twist. Particles can be energized until they radiate across radio-optical X-ray and gamma-ray wavelengths. To human eyes, most of this is invisible. But to telescopes built for different parts of the electromagnetic spectrum, the jet has many faces. In radio light, it may reveal extended structure and motion. In optical light, it may blend with the flare record. In X-rays and gamma rays, it may announce some of the most energetic processes in the system. Each wavelength offers a clue, but none of them alone is enough. That is why modern work on OJ-287 depends so heavily on multi-wavelength observation. The old archive gave the long rhythm. Optical records show decades of brightening and fading. To understand what kind of flare is happening, astronomers must ask how the object behaves across many kinds of light. A disk impact event may be expected to have different properties from a jet-driven flare. A thermal outburst from hot gas may not look the same as non-thermal radiation from accelerated particles. The word thermal matters here, but the idea is simple. Thermal light comes from matter heated to a high temperature, like a piece of metal glowing though in OJ-287. The temperatures and energies are far beyond anything familiar. Non-thermal light comes from processes that are not simply the glow of heat. In jets, charged particles moving at extreme speeds in magnetic fields can radiate in ways that carry the signature of acceleration rather than ordinary warmth. So, when OJ-287 flares, astronomers ask, does this light look like heated disk material, or does it look like jet activity? The answer can change the whole interpretation. A flare at the right time might seem to support the impact model. If the flare's spectrum polarization or high-energy behavior looks strongly jet-dominated, the story becomes less simple. Perhaps the disk crossing influenced the jet. Perhaps the jet produced the flare independently. Perhaps both occurred in the same broad period. Or perhaps the timing model needs to be adjusted. OJ-287 rarely lets one explanation stand alone without pressure. This is where campaigns like Momo become important. Instead of relying on one band of light astronomers watch OJ-287 repeatedly across radio, optical, ultraviolet, X-ray, and gamma-ray wavelengths. They try to build not just a light curve, but a layered portrait of the source's behavior. The goal is to see when the jet dominates, when the disk may be visible, and when the outburst pattern fits or resists the binary model. This is not a simple kind of watching. It requires patience and coordination. The source can change on different timescales. A flare may rise quickly in one wavelength and more slowly in another. The radio emission may respond later than the optical emission. The X-rays may behave in a way that suggests a different region of the system. The gamma rays may suddenly surge, pointing toward energetic activity in the jet. Every wavelength is a witness, but each witness saw the event from a different angle. The jet also carries another kind of information polarization. Light has direction in its vibration, and when light is polarized, that direction is not random. In astrophysics, polarization can reveal the presence and order of magnetic fields. Since jets are deeply shaped by magnetic structure, polarization measurements can help astronomers understand whether an outburst is tied to organized jet behavior. If a flare appears near a predicted disk impact time, but the polarization changes in a way that suggests jet activity, the flare becomes ambiguous. It may still be related to the larger event. A disk disturbance could influence conditions that later affect the jet. But the observed brightness may not come directly from the disk impact itself. The clock may ring and the jet may amplify the sound, or the jet may ring on its own. This is why the simple phrase, repeating cosmic impact, must be handled with care. It is a powerful image, and it may describe something essential about OJ-287. But the actual object is not a clean stage where a single event happens in isolation. It is an active nucleus, a jet source, a possible binary system, a disk, a magnetic environment, and a variable Blazar, all at once. The more closely astronomers look, the less the object behaves like a diagram. It behaves like weather, not weather made of clouds and rain, but weather made of plasma and magnetic fields. A jet can brighten as shocks travel through it. It can bend. It can show knots that move outward over time. It can carry signs of helical magnetic fields. It can appear different depending on observing frequency resolution and timing. Its inner regions may change faster than the broader structure. This weather does not destroy the possibility of a clock. It explains why the clock is so difficult to read. High-resolution radio techniques, including very long baseline interferometry, allow astronomers to look at the jet with extraordinary sharpness. They do not show the system as a simple movie of two black holes orbiting. But they can reveal structure in the jet changes in direction, bright features moving outward, and signs that the central region is far from static. These observations matter because a jet is not merely decoration. It may be dynamically connected to the central engine. If the disk changes, the jet may eventually respond. If the system contains two black holes, their motion could disturb the disk or influence how the jet is launched or oriented. A binary system might produce precession bending or periodic changes in the flow. Separating these possibilities requires careful modeling. The jet is both evidence and interference. That is what makes it such a compelling character in the story of OJ-287. It is not the villain, and it is not the solution. It is the bright, restless foreground through which the deeper system must be read. Without it, OJ-287 might be too faint or too ordinary to notice so well. Because of it, OJ-287 becomes luminous. because of it OJ287 becomes confusing. This is one of the central paradoxes of blazars. They are visible because they are aligned with us, but that alignment means we see the source through its most extreme emission. We are not standing to the side, calmly viewing the disk and central region. We are looking almost into the jet itself. The line of sight is privileged, but not neutral. It gives brightness at the cost of clarity. For the impact model, this is a serious challenge. If some of the major optical flares are connected to disk crossings, then astronomers must explain how those events appear against the broader jet behavior. If some outbursts are jet-dominated, then not every flare can be used in the same way to time the binary orbit. The clock must be separated from the storm again and again. That separation is not always clean. A disk crossing could create a disturbance that later affects the accretion flow. Changes in the accretion flow might influence the jet. A jet flare could occur near the same period as a predicted impact, making the event look blended. Or a jet event could be mistaken for part of the periodic pattern if only one wavelength is considered. This is why modern OJ287 research can feel like listening to overlapping instruments. The disk may play one line, the jet may play another. A possible secondary black hole may set a deeper rhythm. General relativity may slowly shift that rhythm. Observers on Earth hear the combined sound and must reconstruct the score. A single brightening becomes a many-part question. This also explains why disagreements remain. If one team emphasizes the historical optical pattern, the disk impact model may seem especially strong. If another team emphasizes multi-wavelength behavior and jet dominance, the same source may look less like a clean binary clock and more like a blazar whose jet is controlling much of what we see. Both approaches are trying to listen to the same object, but they are weighting different evidence. That is not a failure of science. It is the process of science working inside an unusually complicated source. OJ287 does not need to be simplified into certainty to be fascinating. In fact, the tension between the clock and the jet is what keeps the story alive. The object is compelling because it offers a pattern strong enough to pursue, but a foreground bright enough to question every easy interpretation. The clock may be real. The jet may be hiding it. Both may be true at once. This is especially important as OJ287 becomes a target for increasingly powerful observing networks. Instruments with higher resolution and better sensitivity can examine the jet's inner structure more closely. They can measure polarization track changes, compare emission across wavelengths, and test whether the system behaves as expected during predicted active periods. Each improvement gives more detail, but more detail does not always mean simpler answers. Sometimes better vision reveals more complexity. A blurry image can make a source seem unified. A sharper image can reveal knots, bends, shocks, and changing magnetic fields. A single optical light curve can suggest periodicity. A multi-wavelength campaign can show that different components brighten for different reasons. The closer we look, the more OJ287 becomes not one signal, but an ecosystem of signals. This ecosystem is exactly why it matters. If OJ287 were merely a clean binary clock, it would be valuable. If it were merely a chaotic jet, it would also be valuable. But as a possible binary black hole system embedded inside a blazar jet, it becomes something rarer, a natural laboratory where orbital motion, accretion, physics, relativistic jets, magnetic fields, and high-energy radiation may all interact. The jet that hides the clock is also part of the laboratory. It forces astronomers to build better methods. It forces them to ask whether a flare belongs to the disk or the jet. It forces them to compare old predictions with new data. It forces them to avoid treating one elegant model as the whole truth. In doing so, it makes the study of OJ-287 more difficult, but also more scientifically rich. The listener should not imagine OJ-287 as a broken mystery. It is a layered mystery. At the deepest layer may be a pair of enormous black holes moving in a long, precessing orbit. Around the larger one may be a disk of hot material vulnerable to disturbance when the companion crosses it. Emerging from the central region is a jet brightened by its alignment with Earth, filled with plasma and magnetic structure. Around all of this is time, decades of human observation, billions of years of light travel, and a repeating pattern that refuses to become perfectly regular. The jet sits between us and the clock like a curtain made of fire. But curtains can move. They can thin, brighten, ripple, and reveal shadows behind them. With enough patience, enough wavelengths, and enough returns of the flare cycle, astronomers may learn which features belong to the curtain and which belong to the mechanism behind it. That is the hope. Not that OJ-287 will suddenly become simple, but that its complexity will become readable. By now, OJ-287 is no longer only a point of light that kept returning. It is no longer only a Blazar, or an archive clock, or an impact model, or an uneven rhythm. It is all of these things together. Its difficulty is precisely what makes it valuable. Because if scientists can learn to read OJ-287 through the glare of its jet, they may learn much more than why one distant object flares. They may learn how supermassive black holes move together, how jets are launched and shaped, how accretion disks respond to disturbance, how gravity alters orbits, and how light can carry the hidden history of extreme systems across cosmic time. The jet hides the clock, but in hiding it, it also turns OJ-287 into something larger, a laboratory made not in a human building, but in the deep universe where time, light, and gravity keep leaving clues for anyone patient enough to wait. By now, OJ-287 is no longer only a strange point of light. It began that way as a source that kept returning to brightness across the record of the sky. Then it became a Blazar, a distant active galactic nucleus with a jet aimed almost toward Earth. Then it became a clock found inside the archive, a rhythm assembled from decades of scattered observations and old photographic traces. Then the impact model gave that rhythm an image, a possible secondary black hole crossing the disk of a larger one, sending a flare across billions of years. But the deeper we followed it, the less simple the image became. The clock did not tick evenly. The orbit, if there is a binary system, may be stretched, tilted precessing, and slowly changing under relativistic gravity. The flare was not only a flare, but the visible consequence of hidden motion disk physics, possible delay, and radiation. Then the jet entered the story again, not as a background detail, but as a powerful foreground, bright enough to reveal OJ-287 and bright enough to hide the mechanism that may be producing its repeating outbursts. This is why OJ-287 matters. It is not important only because it may contain two supermassive black holes. It is important because it gathers so many difficult questions into one object. How do black holes grow inside galaxies? How do two enormous black holes behave before they finally merge? How does gas respond when it is disturbed near a region of extreme gravity? How are jets launched, shaped, and aimed across cosmic distances? How can scientists infer invisible motion from timing, color, polarization, and light? OJ-287 is a laboratory, but not the kind built by human hands. There are no walls around it, no instruments placed beside the source, no scientists standing near the disk adjusting conditions and repeating the experiment. The laboratory is a distant active galaxy, and the experiment has been running for far longer than human astronomy has existed. Its materials are plasma magnetic fields, orbiting gas, relativistic particles, and the gravity of objects so dense that light itself cannot escape from within their horizons. The measurements arrive as light. That is the strange humility of the whole story. We are trying to understand some of the most extreme objects in nature, but we do not touch them. We do not send probes into OJ-287. We do not watch the black holes directly in ordinary images. We collect photons that began their journey when the source was in an ancient state, long before those photons reached our telescopes. Each photon is a survivor of distance. It has crossed intergalactic darkness. It has passed through expanding space. It has carried with it a tiny piece of information about the place where it was born. When many such photons are gathered across many wavelengths and many years, they become a record. Not a complete record, never that, but enough to begin asking what kind of system could produce such behavior. This is what makes astronomy so different from most experiments on Earth. In a laboratory, one can often change a variable and watch what happens. In cosmic astronomy, the universe changes the variables and we wait. OJ-287 flares when it flares. Its jet brightens when it brightens. Its possible companion crosses the disk if the model is right on a schedule set not by us, but by gravity. Human beings can only prepare, observe, compare, and revise. That waiting is not passive. Across generations, astronomers have learned to turn waiting into method. They preserve old records. They build light curves. They coordinate telescopes. They observe in radio waves, optical light, ultraviolet X-rays, and gamma rays. They study polarization to trace magnetic fields. They use high-resolution radio techniques to examine the jet. They build models of orbit's disks and relativistic effects, then expose those models to the next return of light. OJ-287 becomes a meeting place for many kinds of patience. There is the patience of the archive, where old photographic plates hold brightness measurements from times when no one yet knew how important they might become. There is the patience of prediction, where scientists wait years for a flare window to arrive. There is the patience of interpretation, where a single outburst may require careful comparison across wavelengths before anyone can say what it might mean. And there is the patience of uncertainty, the willingness to keep more than one possibility alive when the data are not yet simple enough to choose. This patience is part of why OJ-287 remains scientifically alive. A less interesting object might settle quickly into one explanation. OJ-287 refuses. If the disk impact model is right, it gives us a rare possible view of a supermassive black hole binary in action. If the jet dominates many of the outbursts, it teaches us how difficult it is to separate orbital clocks from Blazar weather. If the mass estimates change, it forces astronomers to ask how reliable their methods are. If future observations reveal new structures in the jet or new timing behavior, the story will shift again. The object keeps returning, and every return changes the question. This is especially important for the larger problem of binary supermassive black holes. When galaxies merge, their central black holes are expected to sink toward a common center. Over time, they may form a bound pair, orbiting one another, as the surrounding stars, gas, and gravitational waves carry energy away. Eventually, over immense timescales, they may merge into a single larger black hole. But catching such systems in the act is difficult. The distances are enormous. The separations can be too small to resolve. The light may come mostly from gas, not from the black holes themselves. Some binary candidates may be mimicked by jet precession disk instabilities or ordinary variability. To identify a real pair, astronomers need indirect clues strong enough to survive doubt. OJ 287 offers one of those possible clues: timing. If the repeating flare pattern really traces the orbit of a secondary black hole, then the light curve becomes a map of hidden motion. The outburst times are no longer only dates. They become markers of where the companion may have crossed the disk, how the orbit may have precessed, and how the system may have changed since earlier cycles. In that sense, the flare record is not merely a history of brightness. It is a possible gravitational diary. That diary is incomplete but precious. It may help test how gravity behaves around enormous compact objects. It may reveal whether an orbit loses energy in the way general relativity predicts. It may help constrain the shape of the orbit and the structure of the disk. In some models, OJ287 has even been used to explore deep ideas about black holes themselves, including whether their gravitational fields behave as expected for rotating black holes in general relativity. Those ideas are delicate, and they should not be made to sound simpler than they are. OJ287 is not a magic proof of everything. It is not a clean blackboard where gravity writes one equation in perfect chalk. It is a messy, active, jet-dominated distant source whose signals must be disentangled carefully. But that is exactly why it is valuable. Real cosmic laboratories are rarely clean. They become useful because they force theory to survive contact with complexity. In OJ287, the complexity is the laboratory. The jet is not merely a nuisance. It is a subject of study. The disk is not merely a stage for impacts. It is a physical system with its own structure and response. The possible secondary black hole is not merely a character in a dramatic scene. It is a gravitational actor whose motion must be inferred from consequences. The flare timing is not merely a clock. It is a coded trace of many interacting processes. To study OJ287 is to accept that nature does not separate its lessons for our convenience. This is why future instruments matter so much. More sensitive telescopes, sharper radio imaging, broader multi-wavelength monitoring, and future gravitational wave observatories may all change how OJ287 is understood. Some may reveal more of the jet's inner structure. Some may help identify whether particular flares are thermal or non-thermal. Some may improve the timing record. Some may eventually connect systems like OJ287 to the broader population of massive black hole binaries. The story is not finished because the tools are not finished. Knowledge does not have to arrive all at once. It can come in layers. A pattern can be noticed first. A model can follow. Then a complication. Then a better observation. Then a revision. Then another flare, another test, another way of seeing. The object remains the same in the sky, but human understanding changes around it. OJ287 has already lived through that kind of transformation. It was once only a variable source. Then it became a possible clock. Then a candidate binary black hole system. then a disk impact model, then a jet-dominated puzzle, then a multi-wavelength laboratory. Each stage did not erase the previous one entirely. It added depth. It made the earlier story less simple and more alive. That is how many great astronomical objects become meaningful. They are not understood by one telescope, one paper, one model, or one generation. They are understood through accumulation. A century of light curves, decades of predictions, new instruments in orbit, radio arrays stretched across continents, theories tested, defended, revised, and sometimes replaced. The universe gives one signal, and human knowledge slowly builds an answer around it. With OJ287, the answer remains open. This openness should not feel like failure. It is part of the wonder. A closed story can be satisfying, but an open one can be truer. The goal is not to pretend we know every detail of the central engine. The goal is to see how much can be learned from something so far away, so bright, so hidden, and so complicated. In that sense, OJ287 teaches a broader lesson about cosmic knowledge. Astronomy is often not the science of seeing clearly. It is the science of learning from imperfect sight. A distant point becomes a galaxy. A change in brightness becomes a possible orbit. A flare becomes a test. A jet becomes both obstacle and clue. A timing mismatch becomes a reason to refine the model rather than abandon the search for structure. The imperfect clock is not disappointing. It is generous. If OJ287 ticked with flawless simplicity, it might tell us only that something repeats. Because it ticks unevenly, it may tell us about the shape of the orbit, the strength of gravity, the motion of the disk, the glare of the jet, and the limits of our own interpretation. Its irregularity is the part that keeps speaking. Somewhere in a faraway galaxy, the central engine continues its ancient activity. The disk, if we could stand outside it, would be a region of heat and motion. The jet would be a narrow road of plasma thrown into space. The possible companion black hole would move silently through gravity, unseen except through the consequences of its passage. Nothing in that system is arranged for human understanding, and yet understanding begins. It begins with a point of light. It grows through a record. It sharpens through prediction. It deepens through uncertainty. It becomes a laboratory, not because the universe made it easy, but because the universe made it consistent enough, strange enough, and bright enough for us to keep asking better questions. That may be the final meaning of OJ287 in this journey. It is not only a repeating cosmic impact, it is not only a blazar, it is not only a possible binary black hole system. It is a reminder that the universe can hide motion inside light-time, inside brightness, and gravity inside an imperfect rhythm. It shows us that even when the central event cannot be seen directly, the consequences may still travel outward, patient and measurable, until they reach a world capable of wondering what caused them. For human beings, this is almost astonishing. Our lives are short. Our instruments are recent. Our species has only watched the sky with modern tools for a brief moment compared with the age of the cosmos. Yet by preserving records, comparing patterns, and wading through cycles, we can begin to read a system whose light began its journey billions of years ago. A flare from OJ287 may be an ancient event, but it becomes part of our present when it reaches our detectors. A prediction made today may be tested by light that has been traveling since before humans existed. The future of our observation is in a strange way tied to the deep past of the source. We wait for tomorrow to receive what happened long ago. That is the kind of time OJ287 makes visible. Not clock time in the ordinary sense, but cosmic time folded through distance. The system flares in its own era. The light travels. Human beings build telescopes. The flare arrives. We compare it with the archive. We update the model. Then we wait again. A laboratory made of time, light, and gravity does not give quick answers. It gives returning questions. And perhaps that is why OJ287 is such a fitting place to end. It began as a mystery of recurrence, a light that kept coming back. It became a story about hidden black holes, a possible impact, an uneven clock, and a jet that both reveals and conceals. In the end, it also becomes a story about how science listens to the universe when the universe speaks slowly. The next flare may clarify something. It may complicate something. It may arrive close to expectation, or it may force another careful revision. Whatever happens, OJ287 will remain one of the most remarkable examples of a distant object turning time itself into evidence. Its imperfect rhythm does not weaken the mystery. It gives the mystery its shape. It reminds us that in the deepest darkness, even an uneven flash can become a guide. And far beyond our quiet planet, the Blazar continues. The jet burns across space. The hidden engine turns. The possible clock keeps its difficult rhythm. Light leaves the distant galaxy and begins its long crossing toward us, carrying another fragment of the story. Somewhere in that ancient brightness, gravity is still writing. And here on Earth, we are still learning how to read. And now, as the journey grows quiet again, OJ287 remains far beyond us. It is still only a point of light from Earth, but now that point feels different. Behind it, we can imagine a distant active galaxy, a blazing jet, a hidden engine, and perhaps two enormous black holes moving through a rhythm that no human eye can see directly. What first appeared as repetition became a deeper question. The light returned, but not perfectly. The clock seemed to tick, but the tick's bent shifted and asked to be read with care. That imperfection became the doorway into the whole mystery. OJ287 reminds us that astronomy is often the art of listening patiently to what cannot be touched. We receive light, compare it with old records, wait for the next flare, and slowly learn what kind of hidden motion could have sent it across the universe. Perhaps that is why this object feels so haunting. It does not give a single clean answer and falls silent. It keeps returning, asking each generation of observers to look again, measure again, and wonder whether the next flash will clarify the clock or make it stranger. Somewhere far away, the Blazar continues to burn. Its ancient light is already on the way, and here beneath our quiet sky, we keep learning how to read time in the dark.